So, hello everyone, once again. Today I am going to talk a little bit about dispatchers primarily. Maybe I will remind the formula first. Welcome everyone on the live stream, so you see what I present at the same time if you are live. If you are watching it afterwards, then I provided this stream live. I am doing that. I hopefully will do that quite regularly every couple of weeks so that everyone can ask me a question, and I will do my best to answer those questions. You can ask your questions on chat. You can ask them on Twitter before the stream. Right now I haven't received any questions on Twitter, so I will only answer those questions on chat. And for every stream I have a topic that I am covering while waiting for questions. Today's topic was demanded during the previous stream, so I talked about what is a coroutine. So I also mentioned that Kotlin Coroutines have a mechanism of a dispatcher that decide on which on what thread or on what pool of threads a coroutine is running. I was asked to explain how dispatchers work, because it's actually extremely fascinating what they did in here. The mechanism is non-trivial, but it is quite easy to use it once you understand how to use it. And it is extremely well designed for efficiency, for efficient threads use and reuse. This introduction is a part of my workshop. It's cut out of the bigger section about dispatchers. In this section we are doing much more and covering other aspects of using dispatchers. Right now I will only concentrate on the essential mechanisms of thread management for the default dispatcher, and of course how to use them. So this I hope is a rather basic knowledge to you. We have three main dispatchers. The first one and the one that is used by default, that is used as a standard dispatcher on backend. Also the one that is used by default is the dispatcher's default, nomen omen. It is designed for CPU intensive operations, meaning if you would have different coroutines that are performing CPU intensive tasks, like, I don't know, fitting a model, like a neural network, or processing images, or anything else that is just CPU intensive, they should be running on the dispatcher's default. Yeah. It is having a pool of threads, because our modern computers have typically more than one core. If a processor has multiple cores, it can actually process multiple operations, perform multiple operations, operate on multiple threads in parallel. So at physically the same time, multiple things can be calculated, and the number of those things depend on the number of cores in your computer, and so the most efficient number of threads, if you want to do CPU intensive operations, is the number of cores in your processor. So this is the limit for the dispatcher's default. If you use dispatcher's default, you can use as many threads as you have CPU cores. Why this limit? Because let's say you have 12 cores. If you have 100 coroutines that are CPU intensive, you would need to process them on your 12 cores. If you would limit yourself to operate on 12 threads, this would be optimal, because you would use your processor to the maximum while not generating any additional costs. Every new thread started is a cost. It is a cost of memory. There are different estimates, but most of them say a thread is around a megabyte of memory allocated. There is a cost of starting a thread, of closing a thread. There is a cost of maintaining it, so processor needs to check out all the threads. The more of them are active, the more of like maintenance work the processor needs to do. So the number of CPU cores is the optimal number. However, this dispatcher is only optimal if you use it for CPU intensive operations. Its threads should never be blocked. The second dispatcher, which is the most typical dispatcher for Android developers, is dispatcher's main. Dispatcher's main uses only one thread, which is the main thread. It depends on the framework you are using. It means something else on Android. It means something else on let's say Swing. So dispatcher's main always uses one thread, which is the main thread, and it should be used for all the operations that must be running on the main thread. And as I mentioned, both dispatcher's default and main cannot be blocked, because if you block them, then you cannot block the main thread. It would mean your application being frozen. If you block a default thread, then your calculations are certainly not performed optimally if some of the out of those 12 or less threads are blocked. So it's very, very bad to block those and other non-blocking dispatchers. And here comes dispatchers IO for the help. It's not the only option, we'll discuss it in a moment, but the most basic option if you have some blocking operation, like you need to make a disk operation, or you need to make some blocking call from some library, then dispatcher IO is optimal. There is also dispatchers unconfined, which does not change thread. It doesn't mean it is running on the thread used to start the coroutine. I mean, initially yes, but after it is suspended and resumed, it is running on the thread that resumed it, as I explained in the previous live. So those are the default options. I hope you generally had some understanding of how they work. Now we can discuss in a bit more detail of how do they actually work and how to properly use them. Let me just take a look at the OBS configuration. Okay, because I have some problem with camera after formatting my computer. So if I'm frozen, then don't worry, it happened already. Just ignore it, and I will switch from camera to avatar. So let me show you how those dispatcher actually manage threads, and I will do that with this a bit stupid, but a code that is a bit stupid but useful for us to learn something. We start 1,000 coroutines, and then each of those coroutines we make sleep for a second, and we print its thread name. So when we do that for the dispatcher's default, as I said, dispatcher's default is limited to the number of CPU cores. In my case, it is 12. So I should be able to see on my computer how those 12 threads are printing their names once every second. Of course, finishing this program would take a while. 1,000 seconds divided by 12 threads, it's quite a lot of time, but you can see that there are numbers of those threads. The biggest number is 12. What is a good confirmation that the number of that the dispatcher's default is limited to the number of CPU cores. As I mentioned already, dispatcher's I/O is has a bit bigger limit. However, it is essential to know that dispatcher's I/O is also limited by default. Its limit is, well, its limit is 64. Why 64? I can see 66, but I believe it's by accident. Sometimes some numbers are skipped and we have a bigger number. You can trust me that, I mean, you can see that this is limited because this program is still running. So if it wouldn't be limited, you would have it finished in a second. So you can see it is fighting, and it takes a while. And then why is it limited to 64 threads? You know, there is no good reason for that. I always say it's years of meditations in a forest, and the Holy Spirit went down from the sky. Of course, it's a metaphor. There is an expert number. 64 is just the number that seemed all right. that seemed good enough. So how do we use that? We often use that in some services. I have my GitHub Copilot, so maybe it will help me. So let's say that I have some service that needs to, I don't know, read disk. So disk reader, and yeah, and let's say that this disk reader needs to operate on a file. Open file, some file, reads its content, etc., etc. This is not a correct code, but let's just skip that for a moment. The point is that reading file is a blocking operation, meaning this shouldn't be done on the main thread. It also shouldn't be done on the dispatcher's default. So if we want to, since there is a rule that we want our suspend function to be dispatcher agnostic, to not be forced to start them from a specific dispatcher, what we should do is that we should specify a dispatcher inside this function, and we do that using with context dispatcher's I/O. This is a simple answer. This is what dispatcher's I/O was initially designed for. Now, if this operation is long, maybe it's something longer, maybe it's some request or something else. If this operation is long, you might use all the threads from dispatcher's I/O, all 64 threads. And then the next coroutines will be waiting in queue until they can invoke this operation. What is more, if dispatcher's I/O is used in a different part of your code, over there, you will also be waiting because all the threads are used in here, or the limit is exceeded in here. Maybe I will make sure I have the live still going on. Okay, it seems correct. Okay, I will talk about dispatcher's main immediate slightly later. Okay, so if you use all the whole limit, coroutines will be waiting. But in return, we are sure that we will not start too many threads and drain our device resources. Now, is this dispatcher's I/O limit good enough for our applications. So I would say for Android applications, yes, it is. Because on Android applications, if you need more than 64 threads, then you probably do something wrong. But is it enough for a backend application? I would say probably not. If we have some operation that needs to be made with a specific requests, those requests can happen many times a second, and this operation takes some time, then this 64 is a very small number. What leads to a question, first of all, how can we make a dispatcher with a different limit? And second of all, how can we make a dispatcher that maybe has a smaller limit, but maybe whose limit is independent from this one? Because like if this uses all the threads, the other parts of applications might be blocked, what is very problematic. So how can we still have a limit, but an independent one, to make sure that this will not block something different, which is essential for library creators, because library creators do not want to drain resources, but they even more do not want to cause strange interactions with other parts of our systems. And now to this question, we have an old answer and a new answer. And I will start very quickly from the old answer, and the new answer will introduce us to the topic of how dispatchers manage threads. So the old answer is that we could make a pool of pool of threads by creating executors from executors, new fixed thread executor as coroutine dispatcher. Yeah, this was the old way. And we could use it. It was also a pool of threads with a limit, custom limit, but an independent one. Of course, the problem is that we create a fixed pool of threads, which is a cost. And now there is a new answer, which is still experimental, but it is absolutely beautiful. And to understand this answer, we need to go deeper into how dispatchers IO and dispatchers default manage threads. So I want you first to check out the fact that when you start dispatchers default, the name of the threads is default dispatcher worker and the number. Yeah? When you start dispatchers IO, the name of the thread is exactly the same. Now, why is that? The reason behind it is because both of those dispatchers are actually using the same pool of threads. So under the hood, there is this unlimited pool of threads. Unlimited pool of threads. You can actually see it if you open those dispatchers. This unlimited scheduler, is it this one? I remember I was exploring that, but that was some time ago. So okay, let's keep it metaphoric, but I assure you this is how it works from the usage point of view. So there is some pool of threads which is private in library. It cannot be accessed from outside. You cannot just use this pool of threads. This pool of threads is initially empty, but when there is a demand for threads, those threads are created. When there is a smaller demand, after some time, those threads are killed, removed. And now dispatcher's default is this unlimited pool of threads limited to the number of cores, while dispatcher's IO is this pool of threads limited to 64. In other words, those two dispatchers are using threads from the same pool, but they are having independent limit, so they will never interact with each other. It might remind you of the IT in your company. So let's say that in your company, you can borrow a phone from your IT phone for testing your applications, let's say. However, there is a limit that every team can have up to certain number of phones, let's say 5 phones. So if you have 2 teams, they might have 10 phones together if they both use them to the maximum. But for the majority of time, those teams are borrowing those phones and giving them back. So the IT, thanks to the fact they can reuse the same phones, they can have much less of them than if there would be a separate deposit for each team. So here is a separate deposit for a specific use case. Here we have a shared deposit, which is better managed. Thanks to that, we have the minimal number of threads necessary. Technically speaking, there is also a possible mechanism of limiting redispatching. So you can imagine that if you have a developer who borrowed a phone and so also used one from the limit of the team, if that developer changes a team, he might or she might take this phone, and IT does not need to give it, take this phone and give it back. IT can just, -1 from the one team limit, from the counter of one team limit, and +1 to the counter of the second team limit. The same could happen in here. So when we have a coroutine that is changing a when we have an execution that goes from one coroutine to another coroutine with a different dispatcher, it is technically possible to reuse the same thread, to not redispatch, to continue running on the same coroutine. I think this is not yet implemented because I couldn't observe this behavior myself. I tried to experimented with that in here. No, yeah, you can see, for instance, this worker free switched a thread. In those cases, it is also not necessarily by design, it might be kind of random. So I believe this mechanism, even though I was discussing it with some people from maybe I will not talk about it, but I know there were some such plans to use this mechanism for this possibility for optimization. I think it is not implemented or fully implemented at the moment. However, this is a useful possibility. Nevertheless, the fact that both of those pools are reusing the same pool of threads is a huge huge optimization for threads use. Okay, just let me make it straight. Those two will never block each other. If I start at the same moment multiple processes on dispatcher's default, of course I am limited only to 12. The same can be said about starting more coroutines on dispatcher's IO. So I will be limited to 64. However, what is important, dispatcher's IO and dispatcher's default has separate limits. So when I use them both, I should be able to use 64 plus 12, meaning 76 threads. I can consider bigger numbers right now. Those numbers are not non-deterministic, but this is how it works. So now I told you about making your own dispatcher, and there is a mechanism introduced in the quite recent, I mean, it's not quite recent, introduced 1.5 years ago, but still experimental mechanism. The mechanism is based on the function limited parallelism. So when you create a dispatcher based on another dispatcher, let's say dispatcher's default limited parallelism, you are limiting the number of coroutines that can be used by this specific dispatcher. Yes, so when I start something on D, when I start coroutines on D, I am not limited to 12 threads. I am limited to 4 threads. Yeah? For a regular dispatchers, like dispatcher's default, when I add limited parallelism, I am adding a new limit. So I am still using limit of dispatcher's default, but I am adding a new limit which limits it to additionally. So even if I make a very big number in here, I cannot jump over the limit of 12 threads. Yeah? So it is like making a sub-team inside a team, which is having a smaller limit, but still draining a limit of a big team. However, there is this special behavior, special mechanism of dispatcher's IO. It's the only dispatcher with such a mechanism. When you use dispatcher's IO limited parallelism, contrary to all the other dispatchers, you are creating a dispatcher with a limit which is completely independent from dispatcher IO and directly limits the unlimited thread pool. So if I use dispatcher's IO limited parallelism 1000, my limit is independent from dispatcher's IO, and my limit is 1000. So I will be able to process all those coroutines in 1 second. Yeah, starting 1000 threads. Because this is a special behavior of only dispatcher's IO. Even dispatcher's IO limited parallelism does not have this behavior. Because if I would do something like that, limited parallelism 10, then the result of that is limited to 10, and adding another limits over the previous limit, so it is still only 10. The numbers are, as I said, non-deterministic, but there are at most 10 threads running there. Which is, in my private opinion, quite unintuitive. I absolutely love everything in here, and I think this is absolutely amazing mechanism, except for the naming of this last one. Me personally, I would prefer to make some other top-level function maybe, or a function inside the dispatchers. Maybe something like a new dispatcher with limit. I think it would be a little less confusing. Nevertheless, the current API, which is experimental, so might change. You can see it is still experimental coroutines API. The current API works as follows. And now, why do we have such an animal? So first of all, if you go back into our reader or repository or provider, whatever, which needs to use a blocking function, instead of making a completely new pool of threads and, you know, draining our resources unnecessarily, we could use dispatchers IO and decide how many threads we want this to be able to use. This depends on, you know, on many things. If we believe we have plenty of memory and our core priorities to never make requests wait, we can make it a big number. If we do not want to drain our resources too much, we can make it a smaller number. Now I'm thinking about rather a backend cases, you know. 100 is an extreme number for Android. If this is an Android library, we can make it a small number, 5, 10 maybe. The key point is that this limit will be absolutely independent from the limit of dispatchers IO, so this will not interact with other part of our system. What is very important is that when you define a dispatcher, you should always define it as a separate property. You should never do something like that, because this makes no sense. You are creating a new dispatcher with every call. This means this dispatcher is not limited. Yeah, you can see that. Let's say I use a dispatcher limited to 1, so I have only one dispatcher, the one thread I can use. If I inline it, now I can start thousands of them, because for every coroutine there is a separate dispatcher with a separate limit, so it makes no sense. Okay, so beware of that. Okay, and this is really useful. Another way how this is useful, this is a completely different use case, is for synchronization. So if you have some repository, let's say, that has some shared state, and you do not want to have conflicts, you can use dispatchers IO. All dispatchers main, if you consider it CPU intensive, with limited parallelism 1. So right now you can, you know, safely modify a shared state. Let me show you. So maybe I will make some stupid function, something like that, without dispatcher. If I started in counter, if I started in multiple coroutines, okay, I will have conflicts, and the final let's repeat. I could use a map, or I could use a coroutine scope, something like that. This is a usage of coroutine scope for synchronization. Coroutine scope awaits until everything inside it is finished. What is also something that is generally not well understood by many coroutine developers, what we could cover in a different Q&A. So you can see I should increase that number 1000 times, but because of conflicts, we only have 994. If I used a dispatcher with context dispatcher limited to 1, in a real life application, I don't know what thread it will be. It will be the first one which is available, what is a perfect option, but never more than one at the same time, which is great. And the answer is 10,000 because we eliminated our conflicts this way. So I hope this well describes the difference between those dispatchers, and also describes how they are reusing threads, which for me is absolutely beautiful. This is absolutely amazing mechanism when you use it well. So all the CPU intensive operations on default, all the blocking operations and only blocking operations on IO, all the you know, as we discussed, blocking operations that require an independent limit on IO limited parallelism, CPU intensive operations to the with default limited parallelism that you want to limit. If you use it well, then your threads are just used perfectly. You know, in a perfect application, you have as many threads as you have active cores doing essential work. Different number of threads, which also is managed by limits, waiting for a blocking operations. Everything is optimized in terms of using threads perfectly, which is what we want to achieve, and which is what I wanted to show you. So this was the part that I wanted to show you. I remember one question about the dispatcher's default immediate, but before that I want to check out if I have any other questions. Default use the same. Okay, I hope I answered why do they use the same thread pool to have the you know, the threads reuse for you know, for not starting unnecessary threads and for efficiency. Dispatcher with limited parallelism will not share the same thread pool. Yes, they are all sharing the same pool of threads. Maybe I will add one picture that I like to draw during my workshops. You can see it as follows. So imagine that you have a this pad is a new one. So you imagine that you have a big pool which is unlimited. Okay, and you know, inside this pool, which is absolutely unlimited, you have as many threads in here as you want. You make smaller limits, and you make one maybe smaller limit for default. Okay, I need to get used to this touchpad, and another bigger one for IO. Okay, and when you use default limited parallelism, you are making a limit inside a limit. So you are limited both by default and also by your internal limit, which is, you know, like making a team inside a team. But when you use IO limited parallelism, you are making a new completely independent limit, which, you know, can be much bigger, can be smaller, doesn't matter. It is surely independent. It looks better on real, you know, the whiteboard. Okay. I was asked about dispatchers IO and dispatchers IO immediate. Dispatchers main and dispatchers main immediate. I want to provide some example. So the difference between them is quite minor. However, it can be considered an optimization, which is, you know, generally a good thing. So let me show you an example. Imagine that you started a coroutine. So maybe inside some view model. Just have some, okay, maybe something simple. Inside the main function, no, let's make it view model. It's a typical Android question. So maybe let's make some user view model, okay? And inside this user view model, you have some operation. So maybe on user or on something clicked. So maybe on update user that starts a coroutine on the view model scope. View model scope under the hood is something like that. Supervisor job, dispatchers main. It also has cancellation, and that's it. It can also be something like fun undestroy cancels, and that's what view model scope can be modeled with. And here we launch a coroutine that does a certain things. Let's say start some processes, and in the end it is calling some function, maybe a function which is located somewhere else, maybe a function which is located here, doesn't really matter, but a function update something which is wrapped using with context. It should be rather located somewhere else because it would make little sense to do it in here with context dispatchers main. Okay, so now what is the problem that we are solving? The problem is that we started our coroutine on the dispatchers main, and when you call this function, you are calling with context with dispatchers main. And the default behavior for dispatchers main, actually, I believe it's a default one for all dispatchers. But in this case, it is important that it is the default behavior for dispatchers main, is that when you start a new coroutine, even using with context, by default, you are redispatching. What does it mean? It means that when you call with context, you are suspending the current coroutine, you are starting this coroutine, and inside this coroutine, you are, to start this coroutine, you need to get the thread from dispatchers main. However, if there are other coroutines waiting for the dispatchers main, you are going until the end of the queue. So you need to wait. So if you would, let's say, do something in here like print A, and do something in here like print B, if we would have some other coroutines, I could even model that if I would override main. I could do that if we would have time. But if we would, because I can override main with some, maybe immediate would not work then. I don't know. Okay, it doesn't matter. If I would have some queue for using the main thread, I could have a significant, time difference between printing A and printing B, because after printing A, I am starting a new coroutine and the same dispatcher, but a new coroutine, and so this coroutine needs to go at the end of the queue and wait until dispatcher's main is available. Is this behavior appropriate? I mean, in some way, it is appropriate. However, I kind of agree that it would be a bit more intuitive that if I already am on the dispatcher's main, I should continue on this dispatcher, you know? I should just finish what I do and got it done, yeah? And for that, the dispatcher's main immediate was introduced. It is a small optimization that makes our coroutines not redispatch when not necessary. So in this case, since we are already on dispatchers immediate and we switch to dispatchers immediate, this redispatching should not take place. Now, I believe it is generally considered an optimization. I don't know any case where this behavior should not be appropriate. So I do agree with, I think the majority of our community that is suggesting to just use dispatcher's main always by default. And this is convenient. And by the way, View Model Scope also uses dispatcher's main immediate by default. And I think it is nice. So I would just do that, and you don't need to think about that. This optimization changes very little in our code. It's very hard to show the difference. It only is visible when our dispatcher's main, when our main thread is extremely busy. But this is hopefully a very, very rare case. And if this is not the case, then then you will not see the difference, and it is only considered a very minor optimization, not a very important one, but still an optimization. So better have it than not have it. Okay, what else do we have in here? Yes, I think if you want to use dispatcher's main on Android, I think it is considered a better practice to just use dispatcher's main immediate by default. Why not main scope use dispatcher's immediate? I don't know. I believe it is because it was introduced before dispatcher's main immediate was introduced. I mean, I think the bigger question is why immediate is not the default option. And this is the question it's not me who should answer that. I believe the answer is backwards compatibility, because even if this change is very minor, it would be a change and maybe some applications from the past would start failing, or would start having some problems. So the Kotlin Coroutines team introduced it as a with this separate property instead of just changing the behavior of main. However, when I was checking out what people write about best practices, I think the majority of Android best practices suggested to just use it by default always. And don't think about it too much. There's no need to think about it too much. Okay. Why coroutine interceptor is the only coroutine element of standard library? That's an easy question. Because it must be handled by continuation, which is a part of standard library, which must be a part of a standard library because it's a part of built-in support. So I can tell you a little bit about how dispatchers work in general. Last week I told you what a coroutine is, and this knowledge will be necessary to understand this explanation. So if you not last week, but 3 weeks ago, but in the last video. So if you want to follow, then my recommendation is first to watch that previous live. So you remember that when you resume the coroutine, I don't have this code, I would need to reproduce it. Maybe I have something like that. No. When you resume the coroutine, I should have something nice in here. Yes. So here I show how dispatchers unconfined works. It is not switching a thread. So when you start it on a thread named name1, when you print current thread name, it will be name1. If you suspend this coroutine and resume it from the thread named name2, it will be running on name2. And if you then use a delay and check out after the delay the thread that is running that is the default executor. So the alarm clock used on JVM to resume a suspended coroutine for some time. So this is how dispatchers unconfined work. By the way, I don't find it very useful nowadays. It was useful for testing in the past, but nowadays with new testing tools, this is not very useful. I don't find any usage for that. Nevertheless, good to have it. Maybe one day I will find it necessary to use. Now the thing is that when you use a regular dispatcher like dispatcher's default, IO, or main, whenever you start a coroutine or whenever you resume a coroutine, you are first switching a thread. That's why you are always running. I mean, you are running on this one because it's the only one that was created. If I would make a couple of threads busy, so maybe something like that, global scope, launch thread, sleep. Okay. So I made a couple of threads busy. You can see dispatcher's default is running different of its parts on different threads. Now, how does it happen? It is actually implemented by continuation. When you call continuation resume, let's jump into the coroutine implementation. We need to go deeper. We need to go deeper, and we will do it as follows: suspend func a, println a, delay 1 2 3, println b. We don't need anything else. So if you check out what's there under the hood, you will see that Kotlin compiler creates a continuation instance that is implementing that extends a class continuation impl. And if you check out this continuation, oh my, I don't have it. Okay. If you check out this continuation implementation, I'm very unhappy with the fact I cannot find it. Maybe we'll find it somewhere else. Hey, here. Pam pam. Okay, maybe we'll find. Oh yeah, here we got it. It should have function base. It should have function resume with, which is called when we resume a continuation. And inside this function, there is interception going on. Where is interception going on? Some time has passed since I checked it the last time. Invoke suspended. Maybe it will be easier if I coroutine interceptor. Continuation interceptor. Here it is. So when we create a continuation, before this continuation is created, it is first intercepted, and it is intercepted by the function intercept continuation from continuation interceptor. And this capability is used by dispatchers to transform your continuation from a very simple continuation into a continuation that when you resume, it is invoking this resuming on a different coroutine, on a different thread. So finding an available thread and using it. And this is how this mechanism works, the mechanism of intercepting a coroutine, of dispatching a coroutine or a dispatching. And as you can see, this mechanism must have a very low level support. So it must be supported by standard library and to some degree by our Kotlin compiler. That's why continuation interceptor must be part of the standard library, Kotlin standard library, while other coroutine context keys like coroutine name, like exception handler, coroutine exception handler, like a job, are a part of Kotlin X coroutines library. How coroutine scope function automatically waits for its children? Oh my, we will probably spend a bit longer time than I planned in here. This question can be answered on multiple levels of understanding. I think the simplest answer is that coroutine scope functions like coroutine scope, supervisor scope, with context and with timeout, start a new coroutine and suspend the current one until it is finished. Okay, so this, technically speaking, is a different coroutine than the coroutine that started this, that called this function. And the fact that a coroutine one of the rules of structured concurrency is what I call parents wait for their children. It's a rule that we start understanding when we have our own childrens. We go to supermarket with them, and we shouldn't live without them. Coroutines also cannot finish without their their execution without their children. So once a coroutine is finished its own body, like in here, let's say this coroutine here practically immediately reaches the end of its body, yes? So it could be finished, but it is not. It is just moving from a state active into a state completing. And state completing is when you are waiting in this shop, you are already paid, you have all your groceries, and the only thing you are doing is you are waiting for your children. And this is exactly what happened in here in the state completing. We are waiting until our children are finished, and we cannot finish until our children are done. And that's why after is printed after a second, not immediately, yeah, because parent must wait for its children. And I hope this is a complete answer to this problem. If I would track this coroutine, this coroutine, yeah, if I would track it, so maybe I will track it. Maybe I will do something like that. I will print its state, and I can print its state by getting its job. So here I will print its job, and I will also print, it doesn't matter. And maybe I will do something like that. I will reference this job. Don't do that. I'm a bit ugly thing. I mean, we shouldn't capture job. Or you should better not capture job like that. Right. And I will do that after everything is done. So here the coroutine is in the active state. Here the coroutine is in the completing state. Here, since the coroutine, this coroutine has finished already, the coroutine should be in the completed. Now we can check if my predictions are right. Where is my? Only the number is incorrect, but this is GitHub Copilot who is wrong, not me. I of course knew it will be 671175544, of course. Okay. What is the difference between with context versus async plus immediate await? I mean, the differences are plenty, but we could start with the fact that the async is much heavier concept, because it starts a synchronous process and it awaits it. Coroutine scope only starts a coroutine and awaits it, but async is a heavier concept. The biggest difference is that async requires a scope. Yeah, so here I couldn't replace it with async because async is an extension function on a scope, and well, sorry, that's the biggest technical difference. However, of course, whatever you can use with context or coroutine scope, always prefer using it instead of async and immediate await. I mean, never use async and immediate await. It makes no sense. It's one of the rules of mine I published in the set of rules in the here articles on kt.academy. You can find there the best practices for Kotlin Coroutines. Best practices for Kotlin Coroutines. So I recommend checking it out. I think we are not going to need it anymore. This main immediate create a new coroutine. No, I mean it's a dispatcher, so it a new coroutine is created by either a coroutine builder or coroutine scope functions. Yes, dispatchers, coroutine scope and with context, etc., they all start a coroutine, but that's not a problem. Coroutine is a lightweight concept, and also they start a coroutine which is synchronous, so we immediately await it. It's unlike, you know, launch or async, which starts a coroutine which runs independently. Coroutine scope and other functions of this type start a coroutine which is, you know, immediately awaited. You know, we immediately await its completion, so we often say it is synchronous. The question remains that why was interceptor mechanism added as a standard library, but not... well, this is a more general question. Why do we have a separate library? And this is actually a question that I understand, I hope I understand pretty well, because that's what I would do if I would create such a tool as well. It is, you know, I have a slide for that, so I might use it. There is also a nice chapter in the book. So if you think about what we discussed during the last live, when we discussed what is a coroutine, I showed you, if I remember well, starting a coroutine and suspending a coroutine and resuming a coroutine based on continuation, which is a part of built-in support for Kotlin Coroutines. Yeah, it is part of standard library, part of Kotlin compiler. It's just built into Kotlin. Okay, suspend modifier, continuation interface, etc. Those are very cool things and extremely powerful. They can be used to reproduce absolutely any concurrent style. They are extremely universal, what was proved by many papers. It was also proved by the Kotlin Coroutines team that first experimented. I could read the results of these experiments at some point. Experimented with different approaches to concurrency. They reproduced different concurrency models until they decided what concurrency model they want to use. So this mechanism is very powerful, very generic, however, quite hard to use. You know, if we were to collect continuations and resume them directly, I'm pretty sure our applications will be full of memory leaks. It's just extremely hard to use that. That is why Kotlin Coroutines team introduced a separate library, which is building on top of that, but that is providing a very specific tools, like many tools, functions, classes, like launch, like async, like coroutine scope, etc., which are designed for a certain usage, designed for a very nice usage that really well fits our modern practices. You can actually see it very well that this library is designed for the modern practices. It's designed to be used directly. It's designed for certain use cases, and you know, it makes a lot of sense. So if it's so good, why it is a separate library? It is a separate library, of course, to be able to replace it with a different library in the future, a different library that might be created by Kotlin creators themselves, or a library that might be created by a community. Maybe someone will invent a totally new concurrence style model, whatever. And the fact that it's a separate library leaves such an option for all of us. Yeah? And I don't think it will happen any day soon, but I do believe it will happen one day. Why? Because our practices are changing. Okay, right now we have certain, styles and architectures that we are using, but who knows what will be in 10-20 years. Maybe, I don't know, some totally different model like actors or something will dominate. I don't think actors will dominate, but it's just an example. And thanks to the fact that Kotlin X Coroutines is a separate library, we might not use it and use a different library concretely created based on suspension and etc. Based on built-in support, concretely created for this new concurrency style, which would be, amazing. Or maybe we would explore totally different domains like smart contracts, etc. And they will have completely different use cases. And for those different use cases, the library created for our Android and backend use cases, or front-end and backend use cases, modern, will not fit well. And again, a totally different library will be created. So I think it's a very good decision that those two were separated. What needs to be built into language, what is very universal, but also very powerful, but also hard to use, which is gives a building blocks for the libraries, and a separate library which builds on that and gives us nice tools for everyday usage. I think it's a good decision. Okay, so I reached the last question. So it is time to wrap this live now. Traditionally, if you are looking for a workshop for your company, then kt.academy, the website is literally kt.academy, like the name of the company. All the workshops here are provided by me personally. So for sure, I will be your teacher if you set it up. Also, if you are interested in my books, you can see them here. Kotlin Essentials, which describes the essential concepts of Kotlin pretty deeply. It is based on my other workshops, Kotlin for developers or Kotlin for Android developers. Functional Kotlin, which is about functional aspects or features of Kotlin. Kotlin Coroutines, which, by the way, has second edition. I will show it to you. Available, updated on Amazon already. Pretty big position, based on my workshop, which is covering, I think, everything that developers should know about Kotlin Coroutines, and effective Kotlin, which you probably know already. So, thank you for your attention. Hope to see you on a live, on a conference, or at another occasion, maybe at some workshop. And for now, have a nice evening and have a happy experience with using Kotlin and Kotlin Coroutines. See you.